the spectral theorem. So the spectral theorem is a theorem that describes Hermitian matrices. Now I want everyone to remember, Hermitian is the complex analog of real symmetric. So for a matrix to be Hermitian, its conjugate transpose must equal itself. It's also important to remember, though, that if the matrix is real, Hermitian is the same thing as being real symmetric. So everything we're about to say about Hermitian matrices also applies to real symmetric matrices. So this theorem comes in 3 stages, and the 3 stages ultimately come together to give us a new type of factorization. So let's discuss part 1 of the spectral theorem. The first part of the spectral theorem says that the eigenvalues of every Hermitian matrix H are guaranteed to be real numbers. So let's say that again. The eigenvalues of every Hermitian matrix are guaranteed to be real numbers. So let's see the proof. I think it's actually worth walking through the proof here. If for no other reason, it's a nice exercise in understanding inner products. So here's how the proof is going to go. So the Hermitian matrix we're dealing with is called H here. So to start the proof, we're going to start with a unit vector V in the eigenspace of H, where the eigenvalue we're studying here is lambda. Now, our goal here is to argue that lambda is a real number. So how are we going to do that? Well, the first thing we're going to say is that lambda is the same thing as lambda times the inner product of V with itself. Now, why is that the case? Well, by construction here, we're choosing V to be a unit vector, and the inner product of any vector with itself is always equal to its length squared, which is 1 here. So lambda is certainly equal to lambda times 1. Great. Now, we're going to push lambda into the second slot of our inner product. Remember that we can always push a scalar into an inner product. If we push it into the second slot, we don't have to change the number. But if we push it into the first slot, we have to conjugate the number. Now we see we're looking at the inner product of V with lambda times V. But the whole point of V here is that V is an eigenvector of H corresponding to the eigenvalue lambda. So lambda times V is the same thing as H times V. Now we're looking at the inner product of V with H times V. But remember, the adjoint formula for inner products says that matrices can bounce back and forth inside of an inner product, except every time we move a matrix from one side to the other, we have to take its conjugate transpose. So we can move H from the right to the left here by taking its conjugate transpose. But now the whole point of H in this setup here is that H is Hermitian, which means its conjugate transpose equals itself. So now we're looking at H times V inner product with V. Well, H times V, we already know, is equal to lambda times V. So we've gone through all this trouble to move lambda from the right-hand side of our inner product to the left-hand side. And now we know that we can factor out scalars from the first slot of an inner product, but when we do that, it's not the scalar that factors out, it's its conjugate that factors out. And now we're looking at the conjugate of lambda multiplied by V inner product with V. But again, V in this situation is a unit vector, so the inner product of V with itself is equal to 1. So ultimately, we're just looking at the conjugate of lambda here. So there's several equalities that we went through, but if we pay attention to start and finish, we see that what we've set up gives us lambda at the beginning, which is equal to the conjugate of lambda. And the only numbers that are equal to their own conjugates are real numbers. So this argument tells us that the conjugate of lambda equals lambda, which means that lambda was a real number to begin with. So we started with an arbitrary eigenvalue of this Hermitian matrix, and this argument tells us that that eigenvalue is guaranteed to be a real number. So this is the first part of the spectral theorem. Any eigenvalue of a Hermitian matrix is guaranteed to be a real number. So let's just briefly apply this concept. The first part of the spectral theorem immediately tells me that the eigenvalues of each one of these three matrices are all real. Why are the eigenvalues of my first matrix here real numbers? Well, keep in mind, I'm not telling you what the eigenvalues are. I'm simply saying that I can use the theorem we just proved to argue that the eigenvalues of this matrix are real. And the reason is because this first matrix is a real symmetric matrix. We have numbers on the diagonal, and then since this is 2 by 2, we only have two other numbers which match up here. Real symmetric matrices are examples of Hermitian matrices, so the spectral theorem applies to them. And the matrix in the middle here, this one is significantly more complicated, but if we look at the off-diagonal entries, they all occur in conjugate pairs. 1 minus 3i pairs up with 1 plus 3i, negative I pairs with I, 7 plus I pairs with 7 minus I. So this matrix in the middle is a Hermitian matrix. Its conjugate transpose equals itself. Therefore, I know that whatever the eigenvalues are, they are real numbers. And the third example here, this is a 3 by 3 real symmetric matrix. So again, the spectral theorem applies, and the first part of the spectral theorem says that the eigenvalues of any Hermitian matrix are real numbers. So one of the points of this example, in addition to reminding you what the first part of the spectral theorem says, is to point out that real symmetric matrices are also Hermitian. So anytime we've encountered a real symmetric matrix throughout the whole course, those matrices also are Hermitian and fall under this category that we're studying.